Ainsley, that means you can work on that one, or you can work somewhere else if you'd like. I'll clean that in just a second. And that makes me laugh. So draw me a four-sided polygon. Okay, any four-sided polygon. I would suggest maybe you kind of make it easy to work with. Pretty standard. Okay, and erase anything that's around you. Okay. Come on in, Emily. I'm just asking you to draw. No, there's no signing required. Just go ahead and relax. All I asked you to do right now is to find a to make a four-sided polygon. That's it.
Okay.
What is a four-sided?
This is for you.
Oh, thank you so much.
It's a croissant.
Oh, that's awesome. I was really hungry, so Emily, you have no idea how much this helped me. You're amazing. Thank you.
A four-sided polygon.
Yep. And then now I'm going to ask you this: draw as many triangles as you can from the corner. How many triangles can fit into a four-sided polygon?
Do they have to connect to things?
Yeah. I mean, yeah. Just Emily. Amelia's already got it down. Oh, I'm sorry. It has to connect from vertice to vertice. That's a good question. Meaning corner to corner. Okay, corner to corner. So you have to draw it from corner to corner only. So Alexis, you got it. Okay. And no intersections. So.
What sections?
Yeah, no intersections. So there's like 3 intersections there. So Alexis, how would you draw triangles in a square or in a four-sided polygon that don't intersect?
Just one.
Only one.
Only one.
What?
Okay. How about a five-sided polygon? And I'm a little lost with what you do. Wait.
I don't know. He's drawing triangles in the square.
Yeah, he is. But the triangle.
This is like the area. This is like
area.
No, this is that one.
Okay, a five-sided polygon.
Like that?
No. I think Amelia's already got it down.
Can they come out of the same vertice?
Yes, they can. 1, 2, 3. That's very good. Okay. Thank you very much. That's good. So, my requirement for the triangles is it has to go from corner to corner, but vertice to vertice. So, Matthew, can you help me here? What is vertice to vertice? The last exercise is a 6-sided polygon. How many triangles can you fit?
Oh.
All right. Very, very good. I think you guys are getting this down pretty much. And I'm only going to ask you to go up to 6 at this point. I think it's very tough. 6-sided polygon. This is not easy. Good. This is a 6-sided polygon. How many triangles did you guys find in a 6-sided polygon?
4.
Anybody else get anything more or less? How many did you get in a 6-sided polygon? 4. Okay, that's very good. So you should be able to get 4 triangles. No more, no less. The next question I have for you is not to build me anything else anymore.
Oh.
Okay? I want you now to tell me, inside a triangle, what do all the angles have to add up to? The total angle measure for one triangle. What do you think about a 4-sided polygon?
360.
How did you know that?
Is 180 plus 180 is 360.
Where'd you get the 180 and the 180?
2 triangles.
2 triangles, right? What about a 5-sided polygon?
5-sided. I don't know.
180 times 3.
180 times 3, which would be which would be exactly what Amelia is drawing. No, I'm just kidding. What is 180 times 3? You can actually write out the math too.
540.
Yes. So a 5-sided polygon should have a total angle measure of 540. Okay. How about a 6-sided polygon?
720.
Okay, that's correct. Okay, so what do you notice about the amount of triangles, the number of triangles compared to the number of sides for each of these polygons? Take a look there. Count up how many sides you have and then count up how many triangles you have. What's the relationship consistently? What do you think, Alexis?
There's the number of sides or the number of triangles is 2 less than the number of sides.
Does that work? Is that true? Look at every polygon you've created, count up the number of sides, and then see how many triangles there are. Alexis says there should be 2 less. So if you have a 6-sided polygon, you should only have 4 triangles. Does that hold true? Can anyone disprove that? That's correct, right? Well, you guys have just embarked and created, or not created, but you have just explored our first theorem that we're going to go over today. So now you may have a seat, okay? So you guys proved it yourself. You guys didn't even have to look at any fancy proofs or anything. So over here on this side, they created a fancy table saying this. A triangle has 3 sides. How many triangles are in a triangle, though? Just one. Okay. If you drew a triangle, then you only have one triangle, right? And then you have 180 degrees. Same with what's called a quadrilateral. Okay. If you have 4 sides, you have 2 minus 4, or 4 minus 2, that'd be 2 triangles. So you just simply multiply 180 times 2, and you get 360. You guys can't see it. It was 2 times 180. Okay. And then so forth. It's the same thing. Hexagon, 6 sides. That means it has 2 less in terms of the number for triangles, how many triangles it has. And then you multiply that number by 180, and you get 720, as I think Matthew was able to calculate. The general formula was this. So you can do this for any sided polygon, even up to a 1,000,000-sided polygon. Trivia question, what would a 1,000,000-sided polygon look like, roughly?
It's a really big.
A circle? Let me just try to explore that.
How about cubic?
You guys ready to see my 1,000,000-sided polygon? See, these are a bunch of sides connected to each other. Okay, that's a bad
That's
example.
not enough.
Okay, so let's just do this on a bigger scale. So really small sides.
We can't see any.
You guys can't? Oh, it's frozen? I frozen? Okay. So let's just do this. As you start with rough sides, okay, what is this shape here? That's a hexagon, okay. Let me try to do it. Let's see. Okay, I know that's hard to see, but how many sides is that? That's an octagon.
What about septagon? 7.
I decided not to do that because I can't do that.
Do it. I do one.
Yeah? Can you do how about a challenge, 10-gon? Can you do 10-gon? Yeah.
Do they have to be equal?
Yeah, they kind of have to be, yeah.
Okay.
But if you notice roughly already, the shape roughly becomes less and less like rough. You see, these are like really polygonal. If you do more and more sides, eventually you're going to get to the point where you have so many little equal sides that it kind of roughly resembles a circle. Does that make sense?
12 sides instead of 10.
I don't know if I need you to draw it anymore, though. I'm sorry about that. Sorry. But do you guys see that there? Okay. But for the time being, let's go back to the rudimentary formula. So the formula that you must know for this lesson, or for 8-1, it's really simple. 8-1 is areas of polygons. So you've learned about the area of a triangle. You learned about the area of a rectangle. You've learned about the area, maybe even a trapezoid. But what if we keep going and increasing the amount of sides? This is where things get a little tricky, okay? But the first thing we're going to do in this section is we're going to come up with the general formula for this, okay? So let's see. This is generally what's called, first subsection, this is polygon interior angles sum. Okay? Angle sum. What that tells me is if n is the number of sides of your polygon, okay? Then to find the interior angle sum, all you do is you take n minus 2 and multiply it to 180. So that's it. So if I asked you for, so just a really quick example, what is the interior angle sum of an 11 gon? 11 equal sides. What would you get? So go ahead and work on that very briefly. What do we do? If you need help, then let me set it. What is n? You set up what your n is. Okay. And then 11 gon tells you that there are 11 sides. So n should tell you that there are 11 sides. And then now, what do we do next? Okay. Yeah.
1,620.
1,000. Okay, so you got. So what did you do for the next step?
I subtracted 2.
So you did 11 minus 2 times what?
Times 180.
So you got 9 times 180. Can anybody confirm if that answer is either correct? 1,600 and what?
20.
20. So if you created an 11 gon, it would have the interior angle sum of 1,620. How many triangles can it fit? Does anybody remember that? There you are. So that's where this part comes from. Remember, that just tells you how many triangles there are, and that's why we're multiplying it to 180, because each triangle is 180 degrees within the interior, okay? So just to kind of remind you, that is, again, the number of triangles. Okay, so just as a reminder, I circled the 9, and I just wrote a note to myself that is the number of triangles, okay? Alrighty then, so let's see here. By the way, let's see. This is right. Do the sides or the angles have to be equal? So I don't know, actually.
No.
You think so? I don't know. Let's try this out. Whoops, sorry. Quick check. How many sides, oops, this is not the correct projector. Let's take a look at this example really quick. How many sides are on this polygon here? How many sides are on this polygon?
7.
Okay, so what should be the interior angle sum?
What should?
Yeah, what should it be?
I know. 900.
I don't know. What is it? Tell me out here, guys. Can't just be one person here.
There's 7 sides. So
6 sides is 720.
So it'd be 5.
It'd be 5 times 180.
And that's 900, right?
Yeah.
Check to see if this still equals 900. Double check to see if this is 900. I don't know. And I don't believe you. I don't believe you, Matthew.
Burn.
I don't believe in math. I don't believe in this. I don't believe in you, Matthew. I'll just see if someone else will tell me the answer.
Well, I told you the right answer already.
Did you? Do you have all the right answers, Matthew? I don't know.
Yeah.
Okay. Anybody get this? What is a 128 plus 130 plus 136 plus 134 plus 87 plus 140 plus 145. Did you guys get a final answer? Yeah.
It was 900.
Was it 900? All right, fine. It was indeed 900. So this tells you that your polygon does not have to be equally angled, okay? Right? It does not have to be equal angle measures. It will always add up to however many sides you have times 180. Oh, minus 2 times 180, okay? Challenge question. Challenge question here. What if I gave you this structure? I want you and a partner now to go to the board and solve for x. What do we do now? Okay, good luck. This is going to be your challenge problem. So maybe first start off with what the interior sum should be. Yes.
I know what X is.
No, you don't.
Yes, I do.
No, you don't.
It's 45.
Go home. Really?
Yes.
Let me just double check. I don't know. Okay.
Is it 45?
All right, fine. Go home. I'm just kidding. Good job.
Yay!
Now, how about anybody else that needs? Okay, Matthew, don't just give the answer. Like, help out. That doesn't help. Hey, let me help you by telling you the answer. That's it. You guys, okay, very good. Okay, you guys are set. You guys are very good. Is this just too easy for you guys?
Yes.
I'm glad. Well,
We've done it a bunch of years already.
what? Oh, so this is nothing new. All right, fine, just give up. No, I'm just kidding.
So challenging.
I know you make it more challenging.
Okay, very good, guys.
I know I did it in 17 and pretty sure it's
All right. So, what did you guys get for x? Correct, correct, and correct. The answer is 45. That is absolutely correct. First, you should have done n minus 2 times 180. That should have given you about 360 if our n was 4. And then you set that equal to all these sides combined. 3x plus 90 plus 90. And then you should have gotten x equals 45 once you solve for the algebra. Okay? Now, let's look at something interesting here. What if instead of we doing the interior? I mean, let's go ahead and name the interior. What if this was 90 degrees and this was 60 degrees? What would the other angle have to be?
30.
How did you get it as 30?
Because that's a right angle, so that's 90 degrees.
Uh-huh.
And then that one was 60 degrees. So 90 plus 60, that's 150.
Mhm.
And then you gotta have 30 more to get 180.
Very, very good. Now, let's extend this. What if we extended what's called these, let me see, what's the correct way to do this one? I believe it is, yeah, here we are. What if we had to find the exterior angles?
Isn't it out from the other one? Like,
Oh.
isn't the line of it?
Maybe. Yes.
Isn't it out? Yeah.
Well, yeah, I think it works both ways though, because either you can do this and it's supplementary, or dang it, I didn't want to say that, but yes.
So the top one's to the 120.
How'd you do that?
Magic.
90 plus 30.
What?
90 plus 30.
90 plus 30. Why'd you do 90 plus 30? Oh, what was that? Actually, you guys are using a property. What property is that? Is it
That's exterior.
Angles theorem? Yeah. You remember? Wow, that's really good. You remember that this exterior angle should have been these two added together, right? Or you could have been a little bit lazy like Mr. Wee, be like, oh, that makes a straight line, so this is like 180 minus 60, so this should have been 120 degrees.
Yeah, I probably didn't do that.
However you want to do it, okay?
And should I tell you the other thing?
No,
Okay.
I want someone else, Matthew. That was very nice of you, but I don't want you to keep answering my questions here. Does anybody else know the exterior angle for this? How much this would be equal to? Yes,
90.
90. And then Colton, how about this last one?
That would be 150.
150. How about if you added all the exterior angles together? What should they add up to?
360.
That was awfully fast, Emmeline. Let me see.
It does.
I don't believe you. All right, maybe you're right. Maybe I believe you. Okay.
He's been skeptical all his life.
I'm a skeptic. So that's all the exterior angles. Now, these are just generally just kind of rough notes, okay? There's a little bit less focus on these ones. I'm sorry, so I apologize because I know some of you are very, very good at note taking everything I say. I just want you guys to know these are rough little side notes, okay? Yes.
What would it be if it has 4 sides?
I'll do you one better, Matthew. How about 7 sides?
Yeah, 7.
All right.
Before we get off.
Yes.
Why do all the exterior angles add up to 360?
I was. What are you talking about, Colton? I don't know what you're saying.
I mean, if all the exterior angles, why do they all add up to 360 degrees?
At this point, all I'm teaching you is that that's what it happens. If you want to get to that next step, you are literally entering the college level of math. To prove why these things happen, okay? In order to prove why these things happen, instead of just saying these things happen. All I'm saying to you right now at the high school level is these things happen. When you get to the college level, it's like going back to all that stuff you learned in high school and figuring out why. It takes a few pages of notes sometimes to answer that question, why, okay? So explore that. That means you might be a mathematician in the future. Yes?
I think we already learned the theorem for that.
Okay, fine. All right, well, let's just explore it as if we don't know, Ainsley, okay?
I don't remember exactly, but
No, you're absolutely right, though. So, you don't have to redraw this, but let's just explore this really fast. And if our math is quick, then we can do this fairly quick, okay? So, this is what's in your book. This was 128 degrees. This was 145 degrees. This is 140 degrees. This is 87 degrees. 87 degrees. This is 134, and this is 136, and this is 130. The hardest part is making the exterior angles, so it doesn't really matter which side you choose. You could do this. You do it like this. From here, I could do this. See how it's inconsistent the way I draw my exterior angles? Okay. Just extend one part of the line out. Yes. No, I'm just kidding. Yes. Sorry about that. Here you go. So notice your exterior angles might look a little different from mine, but it's okay. You will always end up with the same answers. Yes.
That top left. What is that?
What, here?
No, the other one.
This
Yes.
128. So just find out the other exterior angles. If let's just say if you decide to do the line this way, you'd end up with the same value. Okay. So if you, I'm just giving you an example. Your exterior angles might not look exactly like mine. This is going to be equal to this anyway. Okay. So it does not matter how you draw it. As long as you draw a line that is exterior, then you're going to end up with the same thing. So find out the measure of this angle, the measure of this angle, the measure of this angle. What that is? Sorry, I should draw it like that, like arrows. Like hey. Measure of this angle and the measure of this angle. We should have 7 exterior angles, okay? For the top right, what would the top right angle be? Yes.
Is that 800 or 880?
That's 887. Oh, hold on, wait, go back. That is 87 degrees. Sorry, that is 87. No, it's 87. Okay, so what is the angle that is exterior to this one here at 87 degrees? At 87 degrees, what is this? 93. Okay, very good. How about this one over here in the corner? Yes?
40.
140?
40, not 100.
Okay, you're confusing me. Okay, very good. How about this one over here in this corner here, in the lower right-hand corner? The lower right-hand corner. Yes. Yeah. Colton.
46.
46. Yes, that's correct. Okay, how about over here in the corner over here? 136. The angle exterior to this. Okay, yes, Matthew.
44.
Okay, Colton, can you help me out with this one over here in this corner?
That would be 50.
Okay. How about over here in this corner?
Is that 186? Is that
That's 128 right here.
128.
Could you help me out, Amelia? I don't know. Thank you, guys. And how about over here?
35.
Now, if you add these together, someone can check with the calculator if they want to be super speedy Gonzalez about this. I'm adding them all up now. All the exterior angles. What do we think it should be equal to?
I think I know.
What do we think?
180 plus the number of sides. No, wait. 100.
Matthew.
Nah.
Why don't you just add them up too?
Okay. I know what it is, but
You're trying to do the math again.
yeah.
So let me just do this then. 8 plus 4, that's 14 plus 4.
4,080?
I don't know. What do you guys think? Okay, so let's do this math. I'm adding all the exterior angles only. And this is 7 sides, right? Previously it was 3 sides on a triangle. And added 360. Let's double check. 3 plus 5 plus 6. That is 14 in my head. Plus 4, that's 18 in my head. Plus 2, that's 20 in my head. Add 2 here. 2 plus 9 is 11. Plus 4 is 15. Plus 3 is 18. Plus 4 is 22. Plus 4 is 26. What did that add up to?
Did I get it wrong? I got it wrong. Okay. Oh, yeah, I got it wrong. Yeah.
So what does that tell us about the number of sides?
Always add up to 360.
It always adds up 360, no matter what. Okay? So that's what is different about the exterior angle as opposed to the interior angles. Okay?
What always adds up to 360? What was
The exterior angles. So what we just kind of went over was this. If you need to write something down next to your notes, you just discovered the polygon exterior angle sum. You did the interior angle sum just a few minutes ago. Now, what you're doing right now is the exterior angles. They should all add up to 360 degrees, okay? Quick challenge problem? Anybody up for it? All right, very good. Sure, I like that. Why not? Why not, Mr. Wee? I'll do it. I'll do it. Okay. Okay, so let's draw kind of a weird, let's see. There's one side here, straight side along here, and then an angle down. Then here, and then here. There we are, okay? Kind of ugly, but it's how many sides is that? That's 1, 2, 3, 4, 5. Now let's extend the exterior angles like this. That's my general shape. It's not too pretty, but it'll do the job. In the corner is 5x, and this corner is 2x. This corner is 6x minus 5. This corner is 3x plus 10. And this corner up here is 2x minus 5 degrees. I want you to figure out the value for x. So you and a partner, or just you by yourself, find a space on the whiteboard and please solve for x.
Does it have to be on the whiteboard?
Yes. Absolutely. Yes.
Can I get one? Is that helpful?
Go ahead. Go ahead. Yeah. Yes.
20?
No.
Is that 20?
Hold on. Yes.
Yeah.
Nice. That's very good. Remember, it's not about the speed, it's about the quality. Okay? So make sure you guys do quality work.
What if you have good quality, but you do it really fast?
Go home. I'm just kidding. I'm just kidding. Very good. Then. That'd be really good. That's a great combination. But quality comes first. Quality, and then with that, with practice, comes speed.
Plus or minus.
That's a -5. Yes, that is a -5.
What if I do it really fast and then check it twice?
Yeah, it's not a bad way of looking at it. Yeah. But with a lot of speed, sometimes you don't know what you wrote.
Well, I check it slowly.
Well, then there's no point in doing it fast. You can check it slowly.
Yeah.
Well,
It's just if you do it fast, you might make a lot of inaccuracies. And then checking over, you're like, I caught this, and then you end up having to write more. But if you do it slow and you just check it, I guess it doesn't really matter. Both has its pros and cons. Either way, just take time on something. Okay, it
what
helps.
if I take time on the test, but go and go really fast, but the homework? Should I leave?
No, I'm just kidding. Stay here. I was just kidding. I'm only kidding you. What'd you guys get? Yes. Yes. X is equal to 20. And there is more formal work here. That's what you should have gone over here. X is equal to 20 degrees. Or just 20. Okay. All right. Very, very good. We're going to move on now to 8-2. You've now mastered the basics of the polygon, understanding the rudiments of the polygon. I'm pretty sure that you've already known that. But let's analyze one specific polygon, a four-sided polygon. Has everyone ever heard of a parallelogram?
Yes.
Parallelogram. Okay, look at my perfect parallelogram. Yes.
That one.
It's
bottom
perfect.
line
It's perfect.
is slightly down a tiny bit.
Fair enough.
In the range.
Fair enough. Well, let's just assume it is perfect. Okay.
Well,
You know how when you assume
All right. Let's see. I'm gonna give these dimensions.
Is this part of your notes?
Yes. This may be part of your notes.
This is 8-2.
Huh?
8-2.
H2.
8-2.
Yeah, this is 8-2. That is correct. That is correct. Okay. I will say this. There's no inaccuracy with this.
What?
I'm not trying to trick you here. This is a parallelogram. What things do we notice about what makes a parallelogram according to the values that you see here? There should be 3 things I want you to find out here. We should come to the conclusion of every parallelogram. What do you see so far? Anybody else besides these 2 hooligans here? I'm just kidding. Quote them first.
Well, it all adds up to 360. At
Okay.
least the angles do.
The angles, okay. We know that from it being a polygon. That is correct. That's one thing I've noticed. What do you say?
The opposite sides and the opposite angles are equal.
Okay, so there we are. Opposite sides and opposite angles, or the opposite angles are, so you say opposite. So let's do this. Opposite sides are equal. Okay, that's 1. And 2 is opposite angles are equal. There's one more thing I'm looking for. Just one more thing. And this one's a little bit trickier to find out what it is I'm trying to look for. Well, what else do we notice? I also know that it's 360 degrees. I know that. Very good. Cool. That is from it being a polygon. There's one more thing. Yeah, what do you think?
The top and the bottom lines are parallel, and then the left and right ones are parallel.
Okay, that's true. Yes. That is absolutely correct. It's not exactly what I'm looking for, but that's true. That is absolutely true. The top and the bottom have to be parallel lines, and the horizontal lines have to be parallel as well. Or else this isn't a parallelogram, right? But what else do you notice here? There's many things that we could notice here, but I am looking for just one. So just let's run through what else we see here. How about these lines and these lines and these angles. What do you guys notice about the relationship between, let's say, these two angles, the relationship between these two angles and these two angles? What do you see, Ainsley?
They add up to 180.
Which is, what's another way of saying something
They're
adds up to?
supplementary.
Yes. So what you can also say is, if the angles come one after the other, we call them consecutive. The consecutive angles are supplementary. This is for supplementary. And I'm sorry, if you needed a title for this note, it's 8-2 Parallelograms. Parallelograms. Sorry. Like parallelograms, okay? Sorry. If you don't know how I just spelled it and I just went chicken scratch on you. Parallelograms, okay? Parallelograms. Those are 3 things that we have discovered. What about, let me see if this works here. Okay. And let's say if this was 19, this was 19, this was 10, and this is 10. If I said this was a parallelogram as well, what would be the measure of all the other angles? What do you think?
90.
How did you know that?
Well, because the opposite one has to be 90, and then there's 360 degrees square.
The angles have
So yeah, so 360 minus 180 equals 180, and the other two have to be equal, and they have to add up to 180.
So
90.
these have to be equal, and they have to add up to 180. Also, what's another way we could have done that?
You could have done it a different way.
with magic.
With magic. It's actually, yeah.
The supplementary angles, since that one's 90, the one down there has to be 90, and then from that one, the next one has to be 90, and then
So forth. Yes, many ways to dissect this, okay? So basically, the one thing is, if your parallelogram, I'm going to write it like this: parallel lines and then O-gram, okay? Has one right angle, then it will end up with 4 total. Right? Sorry about that. Right angles. I always cut myself off. There you are. If a parallelogram has one right angle, then it will end up with 4 total, or 4 right angles total. You can say that. Sorry. 4 right angles in total. Not too hard to understand, huh? It's pretty easy. Yes?
That could have not been a parallelogram.
Can you draw me this not being a parallelogram?
Well, like if you don't know the other sides, it could be like this. Well, on the whiteboard.
Go ahead. Yeah. So try to draw a parallelogram that has 4
No, it
right.
could. You didn't have like the marker thingy showing that it was.
Oh, I see. Based on what I gave, like the given
Yes.
information. Okay, that's correct. That's correct. Yeah. Okay, so the reason why I went through those things is because it's literally in your book, but instead of having to go through hard jargon sometimes of the academic language, you yourself created these conclusions yourselves based on what we analyzed. Okay, it's just saying the same thing. Opposite sides are congruent, except they went one step further. It's congruent, not just equal, but congruent. Opposite angles are congruent. Consecutive angles are supplementary. And that one condition, if you have one right angle, then it has 4 right angles. Okay? So let's see. How far do we need to go from here? Probably... No, I think that's a little bit simplistic. All right, now go on your whiteboard now, okay? On the whiteboard, new whiteboard space, okay? Draw me a parallelogram. Any parallelogram you want, as long as it meets those conditions. Not the 90 degrees, doesn't have to be 90 degrees, right? Make any parallelogram you want.
is good.
Okay, that's fine. That's all right. Oh, it dropped pretty big. If you could. Okay, very good. Now draw diagonals from each vertex. The one vertex. Yeah, for yours it'd be a little bit tough. So from one corner to the other corner, draw. And so let me draw my parallelogram. Now, if you drew it nicely, it should come out right. The theorem should hold up well. And then draw two diagonals, and then make sure it intersects at a point. And just a very brief explanation or a brief relationship here, if you notice it. What do you notice about any of these diagonals? What happened after we drew these diagonals? Is there a relationship between the line segments it made? If I made this A, B, C, D, E, can anybody tell me any relationship between any of these line segments? Like A, B, A, E, A, C.
Well,
What do you see?
AC is equal to DB.
Okay, AC, let me see if that's correct here. Bisect each other.
No.
Does that always work? Does that work for everyone?
Sometimes. Depends.
Okay.
It's a square than it is.
Okay, so that actually does not always apply to all of our.
No.
What?
E is equal to no.
Yeah? What do you see? AE is roughly equal to what?
EC.
EC?
So E is the midpoint of AC and DB.
That's correct.
Okay.
And then, so what's the other one? So, what did you see? Sorry. So E. So you could look at it as AE to EC is equal to EC. What else? So AE is equal to EC or CE, however you want to look at it. I think Amelia's got it already too. And what else did you get, Amelia? What other two line segments should be the same? And that brings us to our. No, please pay attention to the hash marks because we do not know if AE is indeed equal to ED. But in your book here, it says if a quadrilateral is a parallelogram, then diagonals technically bisect each other. Okay? So in this parallelogram, it should be AP is equal to CP and BP is equal to PD. Okay? So I said that here, right? Also, one more thing too is if you drew just one diagonal, do you notice that these two triangles look the same or look equal in measure? Because they don't just look, they are. Okay? This is all this theorem is saying here. Okay? So that being said, let's do a problem now.
There we go.
Oh, I'm sorry. Not so much for the diagonals. I'm sorry. No, I should have been a little bit more formal with that, but we need to move on. So my fault. I should have made more formal notes for that section. But this is more formal here. So here we'll say diagonals of parallelograms. So we're still on 8-2. Diagonals of parallelograms. So if you see any of your other peers in this class, make sure that they actually watch this video, by the way, too. Okay. So because when we come back on this Wednesday or this Thursday, we're going to go right on to the last two sections, 8-3 and 8-4. Okay. So diagonals of parallelograms. And here's going to be an example. It's going to be a bunch of different things. Here's a parallelogram. I'm going to try to make it big. Two diagonals. And then hopefully, let me see if I can. So this would be W in the corner, X, Y, Z. Okay. And you don't have to name the middle one, but we can. We'll just say that's A. Okay. I'm going to write in a different colored pen, which you don't have to do. Okay. I'm going to write in the values of the angles and various sides. Up here is going to be 4R. Over here is going to be 8S. over here is going to be 7s plus 3. And then the bottom is going to be 18. In the corner here, in XYA, in that angle, that's going to be 40 degrees. In the corner here is going to be right here in this corner here, it's going to be 18 degrees. And here is going to be 2t degrees. And I believe that's it. I want you to find R, S, and T. You may work quietly at your own desk for this one. Yes.
I think I got them.
Okay.
I think maybe T. I might have got that wrong.
Right, give me 1 second here. T is going to be. All right, so let's begin here. Anybody get anything for R? What did you guys get for R? Yes, Ainsley.
4.5.
Okay, so how did you set up 4.5?
Well, so the two top and bottom lines are congruent.
Uh-huh.
So they have to be equal. So 4r is equal to 18, and then you just divide 18 by 4.
Okay, so let's double check here. This is what I got for, yep, that's the same thing. So R, you set Wx is equal to Zy, 4R and 18. And you divided both sides by 4, you got R is equal to 4.5. Very good. Anybody solve for S? Yes, Matthew.
3.
Okay, you got 3. How did you set that up?
Because ZA equals AX.
ZA is equal to AX.
8S equals 7x plus 3.
Uh-huh.
And I subtracted both sides by 7x.
Mhm.
And that's S equals 3.
Okay, very good. The last one's actually really kind of tricky. What did you guys get for T? Anybody get anything for T? Yeah, cool.
I got 9.
Ooh, how'd you get 9?
So angle AWX
AWX,
is equal to ZYA.
Nice, ZYA.
2t equals 18, so t equals 9.
How did you know that these two angles were congruent? This actually goes back to older material.
I don't really remember. I just kind of knew.
I'm going to go back to Ainsley. Hold on. Cycle.
Alternate interior angles.
And how did you know alternate interior angles would work here?
Well, because they're on the opposite sides of the
Transversal.
one, yeah. And then they're on the inside of the shape, so they're interior.
And they're in the inside of the shape. And what about the inside of these two lines here? What is significant about these two lines with the transversal in the middle? What are they? Not congruent.
Parallel.
They're parallel. If you have two parallel lines in a transversal, then the alternating angles on the inside, the alternating interior angles, are congruent. Okay? Yes. How'd you do it?
So you said that the lines in the middle of the two sides of your two triangles are equal. And I did CPCTC.
Oh, corresponding.
Parts of
Oh, so you saw as this. Does everybody see that? Matthew saw this triangle, XYZ, right?
No.
No. How'd you do it?
WXY.
Okay, WXY doesn't matter anyway. WXY. Okay, these two big triangles. Okay, this triangle here, WX to Y, and just imagine this. Let's see, this guy isn't here.
Cut it in half.
Cut in half, right? And then over here, I see is WZY, right? And you saw that these two triangles were congruent.
Yes.
And you said you used what? CPC/TC? What does that mean?
Corresponding parts of congruent triangles are congruent.
So these two triangles are congruent, so that means the parts are individually congruent as well. So this corner here is what is it relates to this corner over here, which is a little bit hard to see sometimes. So to make sure you know which parts are actually congruent to which, it's safer to go with alternating interior angles. But if you can recognize it, you can do that too. It's a very, very smart tactic. Okay. All right. Very good. I think I have only one more thing for you guys to go through. So there is a section that I won't go over. Study over the coordinate geometry for this. Okay. The parallels and coordinate geometry. Right. So this is what I won't go over. Okay. So there's a bunch of ways you can prove that a parallelogram is a parallelogram on coordinate proofs. Like you can prove the slopes of the two sides are the same if you think about it, right? Because that means they're parallel, okay? You can also, I think what they did here is that the diagonals, they tried seeing the diagonals bisected each other, okay? So you can also figure out how they did it in here. I'm not going to go over too much in detail. There's a few ways you could have done this too. The only thing that you can't do is angles. Coordinate geometry is not good with angles, trying to measure angles, but it's really good with line segments and distances and stuff and midpoints, okay? The last thing we're going to go through is a proof. Oh, so very good. Oh, give me 1 second. Battery's almost done. We still have about 20 minutes of class, so that means you can try this on your own.
Yeah, boy.
And I would suggest you guys to just look around, talk to each other about this. Like, what do you do, or what do you think? I don't know. I'm a little lost. I don't know what to do.
Notes in the notes or
On the whiteboard, but it may be transferable to your notes.
whiteboard?
So on the whiteboard first. Again, thank you guys for coming to class too. I appreciate this.
Okay.
No worries. Okay. Things are about to get very scary. Okay, they're not scary. Okay, so here, if you need a subtitle, it's proofs using properties of parallelograms.
Which section?
This is still the same section, 8-2. Proofs using properties of parallelograms, parallel signs, ogram. And here's your first proof. It's a giant triangle. It's like an isosceles triangle. You can look at it like that. An isosceles triangle.
Which two sides are equal?
Oh, here, I'll name them. A to C to F. AF is congruent to CF, okay? That will be given to you. So what is given in actual writing, okay, even though it looks like all the sides are congruent, but they're not. What is definitely given to you is that, hold on, actually, yeah, okay, so I'll say this. AF is congruent to CF. I'll give you that. I'm not done, though, with the diagram. I know it's hard to tell, but this is a parallelogram. From A, G, B, and D, what I'm also going to say is this. If you see this in your book, if you see this symbol in your book, written this way, that means that this is a parallelogram. That is given to you right there and then, that this is a parallelogram. If they wrote that in the given statement, that means ABDG is a parallelogram. Your proof, or what you're going to have to prove to me, is can you prove to me that BDG is congruent to angle C? So I'm going to do this in red, color code this in red if you need. BDG must be congruent to angle C. That is your goal. I will give you guys approximately 10 minutes to try to figure this out with as many people as you can. While I eat this croissant. Get dizzy. Always get dizzy. Need a little bit of food. Thank you so much. You have seriously saved me. So go ahead, feel free to move around the class. However you want. You can work on the whiteboard. You can talk with each other. Try to figure this one out. It's not simple. First thing I would probably start with is what kind of triangle are we looking at? If AF and CF are the same. Okay. That's very good. What is the angle that we want to talk about at the very end? We have BDG and what else? In our isosceles triangle, what do we know about that angle?
It's A equals C. Becomes isosceles.
I'm not going to say anything more. Where's the wind right now? Is it too windy outside? Anybody solve it?
Almost. Like 5 seconds.
I said I don't know what like one of the
So yeah.
for this angle to be congruent to that one, like what would the reason be?
Oh, well, think about it this way. They're parallel. Oh yeah, that one's a tough.
Like what's it called?
Oh, okay. Yeah, you just say parallelogram. It's like, or like you can say definition.
I'm done.
Let me see what you got.
Does that mean I got it right or wrong?
That's very good. You guys want me to go over it now?
Is that also right?
Is that right?
Yeah.
Yeah, okay.
All right, guys. Let me go over this. Clear up some misunderstandings here. Any misunderstandings? So, let's take a look at this on a big scale. AF and CF are the same, right? They are isosceles triangles. Okay, like these two sides are isosceles. Okay, what does that mean about the base of their angles? Yes. So if you remember back, the angle opposite to the sides that are congruent are also congruent as well. So when we create the proof, we have statements and reasons. Statements and reasons. Okay. Now, I'm not going to write the given, but you already know the given. It's up here. Okay, so I'm just going to skip that for now. Okay, just going to skip that for now. But the second part here is that we know that AF. Oh, actually, that's already given to us. If AF is equal to is congruent to CF, then what do we know about this triangle? It's an isosceles triangle. So what we can also say is that we can say triangle ACF is congruent. Well, it's not congruent. I'm sorry. It is isosceles. Yes, it is isosceles. Isosceles. And for that, we could just literally say that's because of the definition of an iso triangle. Take it short. Yes.
I wrote AF equals CF for that.
Well, that's what I was going to get to next. Oh, you said AF is equal to CF
Yeah, for number 2.
for number 2? Well, you don't have to.
No, for reasons.
Oh, for the reasons. That's actually understandable too. You can do that. But I think more common you'll see this for people that have been
So I
doing.
should do that instead of.
Yeah, so people that have been doing the math a little bit longer prefer to do something like this. But what you're saying is not incorrect. So people can see that as a good reason, okay? So we also know that the angle, what else about these two angles is that the angle A is congruent to angle C. Again, we could also say that's because of the, or actually, that's actually the isosceles triangle theorem. And I know that's like, wait a minute, Mr. Wee, how come we have the definition of isosceles triangle and then isosceles triangle theorem? If you need to know and you see the formal isosceles triangle theorem, I actually wrote a note. That's on page 374 of your book, around 374 of your book, okay? There is a legitimate theorem saying that about the angles, okay? The definition of isosceles triangle says that there's two sides that are equal, okay? The theorem itself says that opposite of those two sides are two congruent angles, okay? So that's a whole other theorem in itself, okay? Okay, step number 4. So I saw this on Alexis's and as well as Ainsley's and Matt's and Coleman's. You also remembered that A is also equal to D. Angle A is also congruent to angle D. What did someone write for that one, though? What did you write?
Definition of a parallelogram.
You can write the definition of a parallelogram. I think your book might even say that they say it's a property of a parallelogram, because if you remember back and you look back to the book, it didn't actually have a name of a theorem or anything. Like, I'm just going to go back to the book. The book actually just says properties of parallelograms. You can write wherever you want. I will understand what you're saying. And so will a person that's checking work in the future too, besides myself. You can say whatever you want in that case, okay? It's fine. What was the last step, though? Yeah, Colton.
So angle D equals angle C by the transitive property.
Yes. And why is it because of the transitive property, though? Because Matthew says so. Yeah, Ainsley.
Could it be this property of substitution also?
Yep. It could either be substitution or the transitive property. Because you see that A is congruent to C. A is also congruent to D. If A is congruent to C and A is congruent to D, guess what? C and D are also congruent.
Oh my god.
because a substitution, you can literally substitute in C for A in this part here. So at number 3, it says A is congruent to C. You can plug in for A down here. Number 4, you can plug in angle C. Does that make sense for substitution? Or you look at it just transitive property in this logic. If one thing is equal to C, I'm sorry, if C is equal to A and D is equal to A, C must be equal to D. Okay, by logic. That's transitive property. They're almost the same. Okay, that's it for class. So guys, thank you guys so much. Let me give you guys, I don't know if you can need this. These properties that we went over today are a little bit more intuitive, but I do have cheat sheets for this. Okay, I don't think it would really help you on proofs, which is why I make these cheat sheets in the first place, but it might help. For 8.3 and 8.4, I realize I don't have cheat sheets, so please make those, okay? Make cheat sheets for 8.3 and 8.4. I don't have that.
I don't give it to you?
Huh?
I show it to you?
What?
The cheat sheet. You said make a cheat sheet. What?
No, for yourself.
Oh,
If you want to use it for the exam.
okay. Wait, so I can just like make my own notes?
Yes. I mean, I will have to check it, so it doesn't have anything more than just.
So just stuff from the book, like no.
The theorems and stuff. Yeah. So corollary theorems, properties, whatever. That stuff you can write. All right, so I will be trying to post this up on the internet tonight too. So, if you're curious to review this for any reason, okay. All right, thanks for stopping in, guys. Okay, you guys have a great day.